Hey everyone, in this video let's go to question 815 bus routes on Leetcode. This is part of our blind 75 list of questions, so let's begin. So in this question, you're given an array of routes representing the bus route where routes of I is the bus route that the ith bus repeats forever. For example, if route of 0 is 157, this means that the 0th bus travels in the sequence 157, 157, 157, etc. forever. You will start off at the bus stop source, which means you are not at any bus initially. It looks like we're stopping off at a bus stop, okay? So you're not on any bus initially, and you want to go to the bus stop target. You can travel between bus stops by buses only. We want to return the least number of buses you must take to travel from source to target, and -1 if this is not possible. Okay, so let's see what this means for this example here. Okay, so I'll paste in this example here. Okay, so in this first example, so here it looks like we have the 0th bus, right? 0th bus, or maybe let me just write it like this, maybe bus 0 and bus 1. And the stops bus 0 can visit are stop 1, stop 2, and stop 7. The stops bus 1, sorry, I meant bus 0 can visit are 1, 2, and 7. The stops bus 1 can visit are 3, 6, and 7, right? So we have this information here. And source means, so these are like bus stops. So we're basically starting off at the bus stop here, and we want to reach this target here. So the best strategy is to take the first bus to bus stop 7, and then take the second bus to bus stop 6. So how can we do that? Well, this first bus stop, the bus that takes me there will take me to bus stop 1, bus stop 2, and bus stop 7, right? So I will get off at bus stop 7, and then from bus stop 7, notice that this, I can actually travel like 7, 3, 6, and then back to 7. So this is how I can get to 6 again. And so basically here it turns out that this is like the shortest. Do I want to take the shortest amount of buses or? Yeah, so I want to return the least amount of buses. So here it looks like I can just take 2 buses to arrive at my solution. And then I'm not going to go through this one here, but basically you can think about that this one is -1. We can't have it happen. So how might we go about doing this, right? Like, what does this even look like? Well, to me, this kind of looks like a graph type problem, right? Like the reason it looks like that is because we have like a node that is connected to stop 1, stop 2, and stop 7. We have another node that is connected to stop 3, stop 6, and stop 7. And like it's kind of like a circle back to like 7 and then to 1, right? And also from like a circle back from 7 to 3. And so you can think of this as like it's kind of like a graph which has like cycles inside of it, right? So that's fine. A graph can have cycles. There's no problem there. But let's maybe see if we can treat this as a graph problem and how we might be able to solve it using that logic. So in any type of graph problem, we need to know how to represent it, right? Like we need some sort of adjacency list that can represent our graph. So what do we have in this case? Well, let's take a look. We know that from bus 1 we can reach bus 2, or we know that from stop 1 we can reach stop 2 and stop 7. So maybe we can write that down. So from stop 1 we can reach stop 2, we can reach stop 7, okay? Now from stop 2 what can we reach? From stop 2 we can reach stop 1 and stop 7, okay? From stop 3 what can we reach? We can reach 6 and 7. From stop 4, well, we don't have a stop 4, so we will ignore it. From stop 5, we also don't have a 5, so we will ignore it. From stop 6, we can reach basically a 3 and a 7. From stop 7, I can reach 1, 2, but notice how I can also reach 3 and 6, right? I can also reach 3 and 6. Okay, so we have this information here. And now if you think about this, this problem becomes doable, right? Because if I'm starting off at bus stop 1 and I'm going to bus stop 2, I want to basically figure out what is like the minimum way that I can do this in. So I'm starting off at 1 and I want to arrive at 6. Well, what can I do? Well, I can go from 1 to 2 and then 2 to 7 and then 7 to 6. So that's like taking 3 buses. But I can also go from 1 to 7 and then directly from 7 to 6. So that's 2 buses. So maybe if we think of this in terms of like a graph problem, then it becomes easier, it becomes doable. So we still haven't talked about the algorithm to actually go about doing this, but maybe let's go ahead and start off by at least creating our adjacency list. So, we have something to work with here. So let's go ahead and start off by doing that. And so can routes be empty? Yes, routes can be empty. So if routes does not exist, let's just say if not routes, then basically we'll just return -1. And we're guaranteed that source and target is, yeah, I'm guaranteed that source and target is in route. So I don't know if I'm even guaranteed that. So we might have to check that. But anyways, let's first of all see how we might be able to like create this adjacency list, right? So what can we do? Well, basically like this information is given to us in terms of an array, right? We're given 127 and 367. So maybe the first thing we can do is like we can define our adjacency list, default dictionary list, and we can go through the array, right? So for I guess like bus in routes, right? So now we have our individual stops. So bus is like a array. So now we have our individual stops. So what I can basically do here is if I have something like 127, let me just do it. If I have 127, then basically I need to create a couple of connections, right? I need to create a connection from 1 to 27. I need to create a connection from 2 to 17, and I need to create a connection from 7, 1 and 2, right? And 2. And now that I think about this, a list doesn't really make sense here. We can just use a set because we don't really care about order here. So that's like one thing. Now, how might we go about doing this? Well, one thing I'm thinking is like we can just do like a sort of like an n squared like loop on this, right? So what I'm saying is like we can do like I in range 0 to length of bus, right? So this is basically like maybe we can do stop here. Stop might make more sense here. So what can I do? And then I can do for actually let's just start off with I and j. So for j in range, we can do 1 to length of bus. But here it's like we're starting off at 1 and we're looping over these two. And basically I want to add these two to 1's adjacency list. So I can do bus at I dot add bus at j, right? So once I do this and I do this for everything, what's going to happen is I will have these three buses added, right? So let's maybe just go ahead and test that before we move forward. So let me print out routes. Let me just print out the adjacency list, and I'll just return -1 here. And I just want to try out this first value here to kind of see if we see something similar to this. So let's go ahead and do that. And so int has no values. Okay, so this shouldn't be bus at I. This should be adjacency list bus at I. So let me remove this p here. Okay, so let's go ahead and test this. So I just want to see if we form something like this, what I'm after. Okay, so we can see 1 goes to 2 and 7. 2 goes to, okay, so 2 goes to 2 and 7, so that's not correct. So 2 should actually go to 1 and 7. So I guess we have to skip if it's like the existing value, right? So that's one thing we should do. So if I is equal to j, then we can start this off again at 0, and we can just continue here and continue here. Okay, now let's try it out. There might be like an easier way to do this that I'm missing, but this is what kind of just pops to my mind first. So, okay, so 1 goes to 1 and 7, 2 goes to 1 and 7, 3 goes to 6 and 7, 6 goes to 3 and 7, and 7 goes to 1, 2, 3, 6. Okay, perfect. So now we've at least formed our list, right? Like we formed our adjacency list. So now the question is how can we essentially use this adjacency list to travel from our starting node to our ending node? What are some ways in which we can do this? Okay, so one solution that comes to my mind is like a DFS approach, right? A DFS approach, we basically can treat this as a graph, or I guess this is not important anymore. We can treat this as a graph, and then we can do a DFS approach to arrive at the final solution. And then basically like we figure out what the minimum is. Now, DFS approach is possible, but I feel that it might take a little bit long time if we have like a lot of like these nodes here. We have to consider every single one of them, and then like it might just take a long time. So why don't we start off with a BFS approach and see if we can arrive there. And a BFS might actually make more sense here because in a BFS approach, we can like do it like level by level, right? In a DFS, what happens is we'll go from 1 to 2 and then 2 to 7 and then 7 to 6, right? But if we do BFS, we can go from 1 and then we handle 2 and 7 considering like one level. And then in the next iteration, we'll do like actually, we can't do anything in 2, so we'll do 1, 2, 3, and 6. So we'll arrive like right away, right? So just to kind of illustrate what I mean here is, actually, I guess I can just reuse this drawing. But basically, like if we're over here, then a DFS would go like over here, then it might go here, and then it might go here, it might go all the way here, and then it would try that with like another path, etc. So that's useful in some cases, but here actually, we can just process like level by level, right? We just process level by level. And so the first iteration in which we arrive at the ending source or the ending target, that should be our answer. That should be the shortest number of routes. So let's kind of see how we can do that. We've done these questions in the past with BFS. Just another one we recently did was 0-1 matrix or 0-1 maze. I think it's 0-1 matrix. So go ahead and check that one out. But let's see how we can do this. Well, for BFS, we need our queue. We need our scene. Okay, and now what do I want to add to the queue? Well, I want to add in this original route, right? I want to add in this original or the original source. Now, actually, one thing I can check first is if source not in target, if source not in adjacent or target not in adjacency list, then we can just return -1, right? Because I don't think it's guaranteed to be in it, so I don't see that really here that it's guaranteed to be in it, so we can just do that. But anyways, our queue will start off with our source. We will add in, we will do scene.add source, right? So we'll add in our source, and now we can do our queue. Okay, so how do we process queue level by level? Well, we can do something like this. We can find the size of the queue, and then we can only, let's operate only on the elements that are in the queue according to the size. So what that means is that like if we're over here, well basically, so let's maybe consider like a binary tree. I think that's easier to kind of visualize here. But basically, let's say we have these following nodes here, maybe a node here, node here, node here, and all of these are connected. All of these are connected as so. Maybe this is here, this is here, this is here, this is here. If we're doing a DFS approach, we might go all the way down here, right? We might go all the way down here. But really, if we're doing a BFS, we'll first process this, then we'll process these two, and then finally we'll process this. Notice that when we process these two, right, to the queue, we still add in this, we still add in these two values when we are processing this first node, but still we will not process them until the next level, the next iteration. So let's kind of see how that works here. So that's why I take the size and I only process the amount of elements in the queue at this current like size here. So we can expand like breadth first, level by level expansion. So what will I do here? Well, I think what I can do is I can basically like figure out where I am, right? So I guess cur here will be like my bus stop that I come out at. Here I can do cur is equal to, let's see, it will be q.pop0, right? q.pop0. And now I can check if this is actually my target, right? And if it is my target, if cur is equal to target, well then I can just return like my level. So my level is like how many like ripples I've went out. You can kind of think as like this as level 1, level 2, level 3, like that. So I need to initialize level here as 0. And then every time I finish like a queue iteration, I'll increase my level by 1, right? So this kind of dictates like one more distance, one more bus away. Okay, now if this is not the target, then what can we do? Well, let's see in this case, like in this case, if we have 1, then 1 is not the target, right? So then what we want to do is we want to add in the children, we want to add in the neighbors. So we can do like 4. Can we do it? We can do 4. Let's see, route, or yeah, for stop, I guess, an adjacency list of cur, and this should actually be inside this loop here. For stop and adjacency list at cur, well, we can first of all check that we haven't visited this. So if stop not in scene, then we'll go ahead and add it to scene. And then we will go ahead and add it to our queue. Queue.append stop. Right? And that should basically be it. All we need to do for this question. So let's go ahead and run this on our test case to see if I messed up anywhere or if I made a problem. Okay, so now let's go ahead and do some other test cases. Okay, let's go ahead and submit to see if we solved the problem. Okay, so we're getting a memory limit exceeded. So it looks like we're adding in the same node again and again. I think that's possibly what's happening here. So let me see, if stop not in scene, then we'll do scene.add stop. So let me debug this just for a second, see where the problem is. I wonder if the problem is like how we're actually adding this to see if there's a simpler way of doing this. But let me see again. So we do scene.add source, that makes sense to me. And then we're doing something like this. And then we do pop0. And then if it's target, we return this. For stop in this, if stop not in scene, then we'll add in the stop, and we'll add in the stop here as well. Okay, so let me actually take a look at this test case. So, okay, so I think we're adding in a lot of stuff. Probably don't need to do that. Maybe this thing here, like this n squared loop here, is not the best way that we can do this. So we might need to somehow improve this. So let's think of a way that we can improve it. Well, okay, so I think one thing I could do is, let's see, let me think about this and see if I can arrive at a better way of doing this. Okay, so looking at this problem a little bit more, I realized what the problem was. The problem here is that if you think about this, so roots at I.length, right? Roots at I.length. What this means is that this is like the total number of stops. The total number of stops can basically be 10 to the 5. So it can be like pretty large, right? And actually here, routes at I.length, the total number of stops can be pretty large, which means our set here can actually be like exponentially large because like each route might be connected to every other route. So this is why like a map from like stop to stops is actually not the recommended way of doing this. This is the way I initially thought of it, but if you really think about it, we don't actually need access to like all of the stops here, right? Because we can just get this from the routes array, can't we? Well, because if I know, like for example, that stop 1 is part of route 0, well then like I can just look at route 0 to get 2 and 7. So maybe we can think of this problem in terms of like a different approach. So instead of maybe something like stop to stop, what if we do like stop to route, like route ID, something like this. So basically we can store which stop, or store stop map to route. So what this means is like, for example, stop 1 is part of route 0. Same thing for 2. For 7, it's part of 0 and 1. And 3 is part of 1. And then 6 is part of 1 as well. So let's think of the problem in terms of this. And luckily, we don't have to actually modify a lot of things, but let's maybe think of the problem in terms of this. And this actually turns out to be the best approach here. So let's think about this. Well, first thing I have to do is I have to erase this, right? Because I have to create my adjacency list differently. So how will I create it differently? Well, I need to like now map the stop ID to the route that it's part of. So I can do something like this. So I can go through index route and enumerate routes. So for example, here index is 0 and route is like 127. And so route basically has like stop, right? So for stop in route, right? Maybe I can name this like stops actually. For stop in stops. Then what? Well, then adjacency list at this one stop here is going to be like the index that the route is starting at, like that the index that like the route we're on is, which is just index here. So now this will basically make this type of map here, right? Now I don't want to equal it. I actually want to add it because it's a set. So I want to add it like this. Okay. So now we actually don't have to change a lot of things, but basically like down here, right? Like when we are popping, let me just comment this out. When we are popping, we initially popped a stop, right? So here we're actually still popping a stop, but note that we can't look in adjacency list cur because that will actually give me the route index. So what I can do here is I can do like for route ID in adjacency list cur. Now route ID like is 0, 1, 2. It basically is like 0 for this, 1 for this, right? So now I can like get my list of stops that way. So I can do like, what is stop? Well, for stop in, maybe I can do something like stops is equal to route ID at, no, it should be routes at route ID, right? So for stop in stops, now, well, I need to make sure I haven't visited this stop before, right? Like same thing as we did here. So if stop not in scene, then we will add it, and then we'll add it to our queue and queue, right? And so now let's take a look at this approach, which we basically just think about it differently. We just thought about it a little bit differently. So unhashable type list. So for route ID, what have I done differently here? For route ID in adjacency list cur, that seems correct. Am I adding? Oh, I'm adding the queue. That's the problem. I need to add the stop. Okay, so let's go ahead and run these sample test cases. And they pass. Let's go ahead and submit. See what happens. Okay, so it works, but notice it still takes like quite some time, right? It takes like 1.2 seconds. So we can actually further speed this up. And the way we can speed this up is we can notice that, like, for example, if I'm processing like this one here, right? This one over here, then this one is linked to stop number 0, which basically means that in not stop number 0, route number 0. So this basically means that when I arrive at stop number 1, I will try to visit every stop in route 0. So if you think about it, like anytime we like see like a 0 here, we don't have to even visit this. Like we don't have to do this loop here again. We don't have to do this loop here again because if we've noticed that like we've already visited this route in the past, then I don't need to actually visit this route again. If I have stop 1, then I'm going to visit like all of the stops in route number 0. So I can basically additionally also check that I don't visit the route again. So how can I do that? Well, maybe here I can do something like, after this I can do like use routes, and this is a set. And so here what I can do is once like I process all of the stops, then I've used this route, right? So I can do like use routes dot add route ID. And then similarly here, like for route ID in adjacency list cur, to basically stop us from like looping here, if route ID like is in used route. Like if I've already used this entire route before, then I can just continue, right? Then I don't have to actually do anything. So that's another way in which we can like speed it up. So we already like did this correctly, which is like the scene to make sure we don't visit the same stop again. But here it's like to make sure we don't even do this for loop. We don't actually go down the route again. So that's just another way of like improving the algorithm. And so you can think about this approach like where we're actually doing it. So for the time and space one, it's a little bit trickier to calculate here, but like it should just be or like based on the routes and like the number. So you can check the discussion forum for that. But yeah, that was this question. So it helped to like think of it in a different way to arrive at the answer.